Now that we've talked about similar matrices, let's talk about diagonal matrices. So what is a diagonal matrix, first of all? Well, let's just give a definition here. Let's say D is an n by n matrix, and I'll write this as D sub ij, right? For I and j between 1 and n. Okay, then D is diagonal if dij is equal to 0 unless I equals j. So really all this means is every entry is 0 unless it is along the main diagonal, right? So if you'd like to see this explicitly, you could write the matrix as, say, D11, D12, go M&M, D12, blah, 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 D1N for the first row, right? And then DN1, DNN, then you have like D22, et cetera, then everything would be 0 unless it's along the diagonal, right? So 0, that represents a bunch of zeros that I'm too lazy to write, and so does that. Cool. So let's look at an example. Kind of the quintessential example here is the Fedde-Wap diagonal matrix is a 4x4 example, which is 17, 38 along the diagonal, and zeros everywhere else, right? So that'll show up a lot. Spectral theory shows up a lot in quantum mechanics, actually. Eigenvalues and eigenvectors are very crucial and present in the context of quantum mechanics. And a lot of that is due to Fedde-Wap, which is pretty cool. So a diagonal matrix is, that's not a very common matrix, right? If you think about, say, if you were to define a set to be, M sub n, which is the set of all n by n matrices, the set of those which are diagonal would be extremely small, right? And so if we want to be able to use these to simplify computation, right? Because that's kind of the goal here. You can see as a matrix, computation of a diagonal matrix is about as easy as it gets, right? If you're taking the determinant, well, there's so many zeros, you basically just get the first term, the trace is the trace, right? So what we want to do is say, what about an arbitrary matrix, right? Well, we have a way to relate an arbitrary matrix to a diagonal matrix, if possible. And that's the notion of similarity, right? And so if a matrix is similar to a diagonal matrix, we call that matrix diagonalizable. So here's a definition. This will be an n by n matrix. We say A is diagonalizable if there exists a diagonal matrix D such that A is similar to D, right? And so remember, what does similar mean? If two matrices are similar, well, this means there exists an invertible matrix P such that, and we'll say A is equal to P inverse DP, right? This is the notion of similarity of two matrices. It's to see if you can find the existence of this invertible matrix P. So how does the similarity help us in this context, right? Well, if A is diagonalizable, then it's similar to a much nicer matrix. But how does that actually help us, right? Or once we ask how does that help us, before we can figure that out, we have to figure out the settings in which it could help us, right? Because when you're trying to show that two matrices, like two arbitrary matrices, if you're trying to show that those are similar, well, the difficulty of finding that if they're similar, is passed to finding if you can find an invertible matrix P such that, we have this relation here. And not only for diagonalizable, not only do we have to find the existence of this invertible matrix, well, we also have to say, not only that, we also have to find that it's specifically a diagonal matrix that this is similar to, right? So we have two things now that we have to prove the existence of. Luckily, people are smart, and we can state and use the following theorem. A is diagonalizable if and only if there exists an invertible matrix P such that P is equal to, and we'll write this as column vectors x1, x2 through xn, where these are, let's say xi, these are the eigenvectors of A, right? So what this theorem allows us to do is it allows us to only have to find one matrix here, but it tells us how to find it. It says, well, you just calculate the eigenvectors of your original matrix, put them into, augment all of them into some matrix, and then you check if that's invertible. And if it is, the original matrix was diagonalizable. If it's not, then it's not, right? That's why it's an if and only if statement here. More to this theorem, so moreover, A diagonalizable implies that the diagonal matrix that it's similar to is lambda 1 through lambda n, where lambda I, these are the eigenvalues of A, right? So we also now don't have to compute a triple product to find such a diagonal matrix, right? Right, because here what we could do is you could also write D in the context of when you're trying to figure out what the diagonalization matrix of A is. It would be more beneficial to write the similarity condition as D equals, maybe like PA, P inverse or something like this. So let's do P inverse AP, right? And so you use the first part of our theorem that says, okay, it's diagonalizable, great. Well, to find the diagonal matrix that A is similar to, you would have to take the product of three matrices, right? And that's pretty tedious. But luckily, all we have to do is use the first part of the theorem to prove that A is diagonalizable. And then if we do, we don't have to take this product, right? And we will already know what the eigenvalues are, because to find P, we had to compute the eigenvectors, right? So this theorem makes our life a lot easier in a lot of ways. So now let's use this theorem to see how to diagonalize a matrix. And in the process of doing that, really we'll also be seeing how to verify that a matrix is diagonalizable in the first place. So here's an example. Let's say we want to ask if the matrix A given by 2, 0, 0, 1, 4, negative 1, and negative 2, negative 4, 4 is diagonalizable, right? Is this diagonalizable? Well, A is diagonalizable if and only if the matrix P, which is, x1, x2, x3, is invertible, i.e., if and only if the determinant of P is non-zero, right? So to find if A is diagonalizable, we first have to find the eigenvalues and eigenvectors of this matrix A. We've already seen examples of how to do that, so I'll just go ahead and write, and you should verify x1, well, I won't skip ahead that much. You set up the characteristic polynomial, find the roots, you get eigenvalues of lambda1 equals lambda2 equals 2, and then lambda3 equals 6. Then the corresponding basic eigenvectors are -2, 1, 0. X2 is, sorry, that's a negative. And then X2 is 101, and X3 is 01, -2. Well, then P is the matrix -2, 1, 0, 101, 01, -2. And you can kind of see by inspection here, the determinant of P is not 0, which implies A is diagonalizable. And if A is diagonalizable, then we know this implies that the diagonal matrix that it's similar to is lambda1, lambda2, lambda3, zeros everywhere else, which is 2, 2, 6, and then 0, 0, 0, 0, 0, 0. All right, so this is an example of how we diagonalize a matrix. So what I want to do here is split this into 2 videos. This was more of the hands-on side of diagonalizability. You know, what is it? How do we do it? Let's do an example of it. And then in the next video here, which will be pretty short probably, will be more of the theoretical side of the theory of diagonalizable matrices. Okay, I lied about making this 2 different videos because I realized the material that's left is shorter than I had incorrectly remembered. So I'll just splice this together, and then me talking about the next video will just be nonsense. Now, let's find a few different ways to figure out if a matrix is diagonalizable, right? So when we were looking at this first theorem in the first half of this video, this was a theorem that said how we can find if a matrix is diagonalizable, right? We said, well, all you have to do is compute the eigenvectors of the matrix, take the determinant, see if it's 0, right? Or not 0. Depending on the context or the hypotheses that you're given, that may not be the most efficient or convenient way to determine if a given matrix is diagonalizable. So let's look at a few different ways. So we have, let's let A be an n by n diagonalizable matrix. Then this implies, so let's just say, let's make this more grammatically fluent and correct statement. If A is, it's understood that A is n by n. So if A is diagonalizable, then we have that the eigenvalues of A are distinct. Meaning, you know, lambda I is not equal to lambda j for all ij, or it would be more correct, not more correct, it would be correct to say unless I equals j. And that's for all pairs, right? So choose 2 pairs, all pairs are distinct. So how does this help us, right? Because think about the logic of an if-then statement, right? Logic, also a good wrapper. Let's think about the logic of an if A, then B, right? Let's say we have A and B are two like criteria or hypotheses, right? So in the previous theorem, we could say, all right, let's do if B implies C because we've already used A for a matrix and I don't want to be ambiguous here. So let's say if B, then C, right? We can think of B as the statement A is diagonalizable, and we could think about the statement C as the eigenvalues of A are distinct, right? And so what does this mean? This means you get to assume that B is true, right? And then you have to show that assuming B is true implies C is also true, right? This is also B implies C. Well, if we're trying to find a theorem or state a theorem that helps us figure out if a matrix is diagonalizable, how would this theorem help us if that's what we were assuming, right? Well, then it only applies to diagonalizable matrices, but we want to figure out which of those are. Well, this theorem is really helpful for figuring out if a matrix is diagonalizable by understanding the contrapositive of this statement. So what is a contrapositive? It says, right? So again, what is this saying? This is saying if B is true, then C is true. Or B implies C in the symbolic representation here, right? The contrapositive says if C, or let's write it as follows. If not C, then not B. So the contrapositive is still an if-then statement, but it's the contrapositive, right? Not the converse. The converse statement would be to say, the converse would be to say that C implies B, right? So to show an if and only if, you have to show the implication and the converse. The contrapositive is different, and these get confused a lot. So what does this mean, right? How can we use the contrapositive of this theorem? Well, the contrapositive of this theorem says, if not C, then not B. So what is not C? Well, the eigenvalues of A are not distinct. So contrapositive, so here's the theorem, but contrapositive. Let's say lambda I equals lambda J for some I not J. This implies, right, that's not C. That means there exists an eigenvalue of at least multiplicity 2. Well, then not C implies not B. And what is not B, right? That means A is not diagonalizable. Okay, so what we can do with the contrapositive is we can compute the eigenvalues of a given matrix, see if there are any repeated roots of your characteristic polynomial, and then that right there determines if your matrix is diagonalizable or not. So that's very beneficial. I wanted to give a quick example. Take A, which is 1, 1, 0, 1. You can quickly compute that lambda 1 equals lambda 2 equals 1. And so this implies by the theorem that A is not diagonalizable, right? So just a quick little example there. The next thing I want to do, the last thing I want to do for showing some ways we can compute when a given matrix is diagonalizable is to define the eigenspace. So let's figure out, well, let's first define what an eigenspace is for a given eigenvalue, and then let's see how we can use this so-called eigenspace to figure out if a matrix is diagonalizable. So let's give a definition here. Let's let A be an n by n diagonalizable, well, for the eigenspace, it doesn't need to be diagonalizable, excuse me. This is an n by n matrix. Let's say for eigenvalue lambda, the eigenspace is defined as follows. So E sub lambda of A, and it's defined to be the set of corresponding eigenvectors, right? So it's the set of eigenvectors for that given lambda. So that's X in n-dimensional complex space such that AX equals lambda X, right? So this is the eigenspace, and you'll have an eigenspace for each eigenvalue, right? So what do we get here? We get this following theorem. A is diagonalizable if and only if, right, which is an if then, and the converse if then, if and only if the dimension of the eigenspace of a fixed eigenvalue lambda is equal to the multiplicity of lambda. And so the multiplicity of lambda being the dimension of the eigenspace guarantees that you have enough eigenvectors, unique, right? So we won't probably use this all that much, but it's still worth defining the eigenspace. That's an important concept in spectral theory, and how we can relate it to diagonalizability. Okay, so I think that's all I want to say for now. In the next video, we will do a couple examples in spectral theory that we have not yet seen.